All right, so we're going to change to a new topic here. We're going to look at Introduction to Vectors. So this is lecture 19 of 95, so we're getting through them. 19 is a factor of 95. We're 1/5 of the way through it, so getting there. This is an overview of the entire sort of vector knowledge you'll need for specialist maths. Some of the prior knowledge for this will be linear relations and algebraic techniques, the basics of matrices and Pythagoras' theorem. But I'm assuming that if you're looking at this, you've got a pretty sound foundation with some of the prior concepts that you need in order to be doing specialist maths. Anyway, so what we'll cover in this video is what is a vector, how do we find the magnitude of a vector. We'll look at some vector addition and subtraction, scalar multiples of a vector, and the zero vector, parallel vectors, the position vector, operations on vectors, the linear combinations of vectors, and then we'll finish up by looking at linear dependence and independence, which is probably the most challenging part of this. So let's jump into it. Let's have a look at what a vector is. So we can think of a vector as just being a directed line segment. So you can see here we've got a line from A to B pointing in a certain direction from A to B, and it's got a certain length, right? So we would call that a directed line segment, AB. And the way we notate that is writing AB and then we put an arrow on top. And then we could also represent it using we could represent it as a column vector, which we use a 2x1 matrix in order to do that. So this vector AB would be, as a column vector, would be 3, 4. So 3 would be in the first row, first column, and 4 would be in the second row, first column. And so this top number tells you how much to the left or right you're going. In this case, we're moving to the right 3, and then we're going up 4. So it'd be 3, 4. And then as well, the way we would notate that would be with this sort of bold V, bold italics V for this vector. Okay, so what we could say is the magnitude of the vector. So the way we denote the magnitude is we put these these vertical lines either side of the notation. We could have put it either side of this V as well. But I think you would agree, if we wanted to find the magnitude, the word magnitude just means length. So we're just going to find the length of this line. I think you would agree that every vector, if it's just got a line, a direction, and a length, then it's going to form a right angle triangle. So we can just use Pythagoras' theorem. So it's going to be the square root of x squared plus y squared, which is the square root of 25, which is just 5. So we would say that the magnitude of the vector is 5. Let me just fix that. Yeah, so we'd just say that the magnitude of vector v is 5. I've just sort of swapped between notations there, just so you get the idea. But you decide what kind of notation you'd like to use, and obviously depending on the question that you're answering. But yeah, that is what a vector is. It's got a size and it's got a length, and sorry, it's got a size and a direction, and that's the two factors for it to be a vector. Okay, let's have a look at vector addition. So now let's consider if we've got two vectors. So we've got this vector v here, and then we've got this vector u here as well. If we wanted to add them together, the trick is that you add the tail of the second vector to the tip of the first vector. So you can see that the tail of vector u is at the tip of vector v. So that goes like this. And you can see we get this resultant vector is v plus u, and that goes from A to C. And we can see that sort of creates that vector there. So yeah, we say that vector AC is equal to vector v plus vector u. If we were to look at sort of a concrete example, if these happen to be two column vectors, in fact, v is the vector 1, 3, because we move across 1 and then we go up 3. Across 1, up 3, and then u, we go across 3, 1, 2, 3, and then down 1. So that is this situation here. And if we're adding them as column vectors, we just add the elements together, just like you do when you add matrices. So 1 plus 3 is 4, 3 plus -1 is 2. So you end up getting this situation going on. And yeah, that's how you do vector addition. Again, tail to tip is sort of how you remember how to add them geometrically. Okay, let's have a look at scalar multiplication. So if you want to multiply a vector by a scalar is just some real number. It changes the length of the vector for some n element of real numbers. So up here, we've just got a slider for n. At the moment, we've got some vector just pointing in space, just randomly made up. N, if we change that, is just going to scale up or down the size of that vector. So if we have 2v, then it's just double the length. If we have 0v, then we've got what's called the zero vector. Because if you multiply a vector by 0, you just get what's called the zero vector. And the way we denote the zero vector is with a bold 0. And it represents a line segment of 0 length and no direction. And as a column vector, we would write the zero vector as 0, 0. This is obviously for 2 dimensions. But I hopefully think you can imagine we could also move into 3 dimensions with vectors. We wouldn't just have an x and y coordinate, we have an x, y, and z coordinate. In any case, we can also have a scalar being negative. So if we were to take n to be -1, that makes the vector point in the opposite direction. So just to recap there, if n is 1, that's just some vector, v. If we make it -1, it points in the directly opposite direction. We can obviously make that as big or as small as we like. So that is scalar multiplication and the zero vector. All right, let's have a look at vector subtraction. So vector subtraction is just like addition, except you're adding a negative vector, right? So if you wanted to do v minus u, what I think you would agree is that's the same thing as -u plus v. So that's just how numbers work as well. For example, if I did 3 minus 2, that's the same as -2 plus 3. So they sort of work the same as numbers in that sense. Let's have a look at this example here. So we've got this vector v and this vector u. Currently, we're adding them, and it gives us vector v plus u, just like we saw before. But if we make u negative now, if we make u -1, so now u is over there like that. Now this vector here is v minus u because we've taken v and we've subtracted u. Remember, -u or -1u just points in the direct opposite direction as u. So we sort of get that situation going on. Just to sort of show you that again, that would be vector v plus u, but we make u negative, so it's going to point in the opposite direction. So now this is -u plus v, alternatively v minus u, same thing. So yeah, that's how you do vector subtraction. You just take one of your vectors to be negative and then add it on, just like before. Okay, parallel vectors. Okay, so parallel, just recapping the idea of parallel, hopefully you're aware, two things never touch, like train tracks, right? So two non-zero vectors u and v are parallel if there's some real number k that's not 0, such that u equals kv. Yeah, so what that means is they're going to be parallel if one vector is a scalar multiple of the other, right? So if we look at these vectors here, v and u, we can see that they're parallel just sort of by looking at them, but we can also see that vector u is a multiple of vector v. And so that means they're parallel. They're sort of pointing in the same direction, right? Now remember, with vectors, it doesn't matter where in space it is, right? So for example, you know, they could be on top of each other and they'd still be considered parallel, right? Like if that's on there, those vectors are still parallel. So yeah, if one vector is a scalar multiple of the other, then they're parallel. So for example, if we were to do it using column vectors, if vector v was 3, -2, and vector u was 9, -6, well, then we can see that if we multiply vector v by 3, well, 3 times 3 is 9, 3 times -2 is -6. So we can see that u and v would be parallel vectors because U is a scalar multiple of V. In this example, K is 3. Okay, that's parallel vectors. Let's look at position vectors. So let's just look at position vectors in 2 dimensions. So just ignore the right-hand side for now. So a position vector is basically this idea that if we have a point in space and in 2-dimensional space, if we take a vector from the origin to that point, we call it a position vector. So if we have OA, if we have the point A rather, the point A here is at 3, 4, x coordinate of 3, y coordinate of 4, and then we draw a vector from the origin to that point, we would call that a position vector, and it would have, we've moved across 3 and up 4. So as a column vector, it would be 3, 4. And more generally, if you had any point in 2-dimensional space with an x coordinate of A1 and a y coordinate of A2, then your vector would have this form where you would say the vector A equals A1, A2. Okay, and so now we can actually look at the other side here. I just want us to move into the 3rd dimension now. So now we've got 3 dimensions to consider, sort of length, width, and height. And yeah, we're in the 3D viewer here. So before we go into 3D, let's just look at what we're looking at here. We've got the 2D, we're sort of looking down at it at the moment. So we've got X to the right and Y up, just like over here. And so this vector A is the same as this vector A here. We're sort of pointing along to this point 3, 4. Okay, and then what we're going to do is, all right, we're going to say, all right, in 3 dimensions now. So let's consider some point in 3-dimensional space. So the point is going to be, it's going to have an x coordinate of 1, a y coordinate of 2, and a z coordinate now of 3. So if we come into 3-dimensional space now, you can sort of see that this point B, as I said, has a x coordinate of 1, a y coordinate of 2, and a z coordinate of 3. And so more generally, we would say that B is for any point in space with x coordinate B1, y coordinate B2, z coordinate B3, then your vector is equal to this column vector, right? And so yeah, that's that vector there, B, which we've got sort of in orange. So yeah, that's what a position vector is. You're sort of just pointing out where its position is in space relative to the origin using a vector. Okay. All right. Properties of basic operations on vectors. So vectors actually work a lot like algebra. So you've done a lot of algebra by this stage, I imagine. There's a bunch of rules that you probably apply unknowingly at this point, but things like the commutative law. So A plus B is equal to B plus A. So 2 plus 3 equals 3 plus 2 in number land. But similarly in vector land, vector A plus vector B equals vector B plus A. Okay, I've actually made another video on this, so I'll put a link in this part of the video, but also below for you to go and watch that, where I talk through all of these properties of basic operations on vectors. But yeah, for most of these, they're just an extension of our algebra laws, and they work in vector land, if you will. So something like this: there's the A vector plus the 0 vector just equals the A vector. In number land, we just have 2 plus 0 equals 2. Okay. So yeah, I'll put a link for that if you want to go and watch that and want to explore each of these in more detail, because I've sort of shown each one with a picture elsewhere. So feel free to go do that. Okay, now it's getting a bit more interesting. We're going to look at linear combinations of vectors. So let's talk about the definition of a linear combination. So a vector W now, let's say, is a linear combination of vectors v1, v2 up to some vector vn, if it can be expressed in the form W equals k1 by v1 plus k2 by v2 plus all the way up to kn by vn. Okay, where k1, k2, and kn are real numbers. Okay, that's all a bit confusing, but let's break it down. Let's for a moment imagine we've got some vector v1 and we move to the right one and up 2. So if we're sort of starting at this point here, move across 1 and then up 2, that's this vector v1 at the moment, okay? Similarly, v2, you move to the left 1 and up 1. So you move to the left 1 and up 1. So that's this vector here. Okay. If we were to add those vectors together, we would get V1 plus V2. Okay, at the moment, K1 and K2 are both 1. So that's what we've got here. Now, just to recall, if we're to add V1 to V2, we take V2 and add it to the tip of V1. So we take the tail of V2 and add it to the tip of V1. So we would sort of point here, and then we would connect the tail of V1 to the tip of V2. So you would end up with this red vector here. So this red vector here represents V1 plus V2 at the moment. Okay, but what we're saying now is we can actually express another vector W as a linear combination of these two vectors. So let's just look. The vector W is negative 1, 7. So we start at some point, we move to the left one because that's negative 1, and then we move up 7. So that gets us to here. So this is vector W. But what you'll actually notice is we can express W as a linear combination of V1 and V2. And the way we would do that is we need two groups of V1. So we're going to change this one to be a 2. That gets us to there. And then we need three groups of V2. We make V2 3 times as large. So we get something like this. And what you'll notice now is the addition of V1, of two groups of V1 plus three groups of V2 would now give us this vector here, which moves to the left one and up 7, which is the same as W. So that's what it means for something to be a linear combination of other vectors. So vector W is the linear combination of vectors V1 and V2 because it's two groups of V1 plus three groups of V2. Okay, where 2 and 3 are scalar coefficients, K1 and K2. So that's what it means for something to be a linear combination of vectors. Okay. Yeah, and obviously, we can combine them in different ways. K1 didn't have to be 2. If we needed it to be equal to W, it did, but you noticed along the way, we get all these different vectors that we can form as we move things around, which I think is pretty cool. Okay, so there you go. All right, let's have a look at the next thing, which is where it's going to get a little bit more interesting. Okay, so we're going to talk now about what's called linear dependence. And let's just look at the definition for now. So a set of vectors is linearly dependent if at least one vector can be written as a linear combination of the others. So linear combination in term, just like what we spoke about, you have to be able to express some vector as a combination of other vectors, as a linear combination of other vectors. So let's look at an example. Let's look at the two vector case, just to sort of wrap our heads around what's going on. So if we've got two vectors in space, A and B, we say that they're linearly dependent if there exists a real number K and L that are both not 0, such that Ka plus Lb equals the 0 vector. K multiplied by the A vector plus L multiplied by the B vector equals the 0 vector. Now, this is an important thing to say as well. Essentially, vectors are linearly dependent if you can combine them in such a way that you get the 0 vector. And that's true in higher dimensional spaces as well. So that's true in 2-dimensional space and 3-dimensional space and so on. So we'll go into this idea a little bit more because we sort of spoke briefly before about how sort of our algebra rules apply to vectors, and that's no different here. So if we say that L is not equal to 0, because we're saying, let's explain why we're saying they're not equal to 0. If L and K are both equal to 0, then 0 plus 0 gives us the 0 vector. So that's a trivial solution that we're not really interested in. We're interested in a situation where not both K and L are 0, because then you're getting something a bit more interesting. So if L is not equal to 0, we're going to take this equation and we're going to divide through by L. So if we rearrange this equation for vector B, we get that vector B equals negative K on L multiplied by A. And so what we've shown is that B is a scalar multiple of A, meaning that the vectors are linearly dependent. Because we said before, if you can express one vector as a scalar multiple of the other, then they must be parallel to one another. And the same logic applies if you rearrange for A. If K is not equal to 0, then vector A equals negative L on K multiplied by vector B, and this demonstrates linear independence as well for the same reason. Okay, as I just mentioned, if both K and L are 0, this holds true. It's just like saying the 0 vector plus the 0 vector gives you the 0 vector. So that's obviously the case. But that case is uninteresting. It's just like 0 plus 0 is 0. It's not an interesting fact. Okay, so what we can conclude is that a set of two non-zero vectors is linearly dependent if and only if the two vectors are parallel. So what we've got here is two vectors, and let me just put them back to one for now to explain what's going on down here with this image, and I won't be able to get it to one because there we go. Don't breathe, and it'll stay there. Okay, so we've got two vectors. This vector here is vector A, or one group of vector A, and this vector here is vector B. This vector over here in red is vector A plus vector B. I should say more specifically, it's K, which is some value we can change, K multiplied by vector A plus L multiplied by vector B. So as you probably saw, as we change K, we're changing the size of the red vector, right? And so now, if you were to add two groups of A plus one group of B, you'd get a vector like this. Okay, and what this is saying here is if we can get a non-trivial solution, so values of K and L, where we can get the zero vector, this red vector to go to zero, then they are linearly dependent. So if I have a play around here, I bet I can make this go to zero. Okay, other than when K is zero and L is zero, because that solution sort of doesn't count, right? K is zero and that's zero. We sort of just have a boring solution. We're not really interested in that. But I reckon we can get one when they're not zero. And if we do this, I think you'll see. So there you go. If K is negative 0.5 and L is 0.5, then when you add those vectors together, they're going to cancel to be the zero vector. And so you've satisfied this equation because negative 0.5a plus 0.5b is going to give you the zero vector in this case because these vectors are parallel. So that's what linear dependence is. Let's show sort of the counter example so you see what linearly independent things look like. So linearly independent is when we basically can't change the values of K and L such that we can get the sum of them to go to the zero vector. So here we go again. We've got some vector A and we've got some vector B. I guarantee you now, other than when K is zero and L is zero, I'm not going to be able to get these. I'm not going to be able to get this to go to zero. Remember, 0, 0 doesn't count. But because vector A and vector B are not parallel, I'm not going to be able to get these to go to zero, which means they're linearly independent. So I think that's pretty cool. Obviously, when it's 0, 0, it works, but there's no other time when I can get them to go to zero because they're not parallel. So yeah, it's not going to work as we spoke about from before. So a set of vectors is linearly independent if no vector can be written as a linear combination of the others. Okay. All right, let's have a look at the last thing, which is the three vector case. So we just looked at the two vector case. We sort of got two vectors and we're trying to work out if they're linearly dependent or independent. Let's look at the three vector case. Okay, and again, the definition is the same. A set of vectors is linearly dependent if at least one vector can be written as a linear combination of the others. So if we look in this instance, we say three vectors A, B, and C are linearly dependent if and only if there exists a real number, K, L, and M, not all zero, such that K by A plus L by B plus M times C equals the zero vector. Okay, and so what that means sort of geometrically, I think it's important to have an intuition for that. If you just ignore the red line for now, I'll explain what that's doing in a moment. But if you look at these points in space, see these black arrows? This point here, and this point here, these are all position vectors that we've drawn to those points. But you'll notice we've sort of got this blue plane that's sort of sticking out. And I think you'll notice if we get the angle right, all of those points are on that plane. Okay? And what I'm going to do is I'm going to scale those vectors up and down. So I'm going to change the value of K. And what you'll notice is, again, ignore the red one, but what you'll notice is we're not going to get off that plane. No matter what I do, I can change these values But those black lines, those black vectors are always staying on this plane, which in three-dimensional space means that they are linearly dependent because we can't span three-dimensional space. We can't get to every point in space. We're sort of stuck on this plane, just like just like in two dimensions, when two vectors are parallel, you're sort of stuck in that line in space. In three dimensions, you're sort of stuck in this plane in space. Okay, now let me just go one step further and explain this red line now. This red line is K multiplied by vector A plus L multiplied by vector B plus M multiplied by vector C. So what we've done is we've essentially just added these three vectors together. And you'll notice as well that that red vector is also stuck on the plane. So it's the sum of them. And we know just from what we spoke about before and what it says here, we should be able to make that red vector go to 0 because these vectors are linearly dependent. So if we get this right, probably going to stuff it up. Obviously, other than when everything's just 0, right? So we've got to find an example. I did it before. I'm getting close. We need that red one to go to 0, and we're getting close. Somewhere around there, maybe. I think you get the idea. That red vector has gone to 0 when these values are something like that. There's other values I could have picked as well, but you can see that that red vector equals 0, and K, L, and M are not just equal to 0. They're not all 0. Okay, so I think that's interesting to have a sort of geometrical understanding of what it means for linear independence for three-dimensional vectors. And in this case, yeah, we looked at a three-vector case. We could have looked at a three-vector case in 2 dimensions, but yeah, we looked at it in 3 dimensions just to sort of get a feel for it. Okay, just some final things to be aware of. So any set that contains the 0 vector is linearly dependent. And that should make sense. If you've got the 0 vector, you've got some, so when we say set, we've got a set of vectors. One of them is the 0 vector. And we've got some other vector there. We're always going to be able to combine them such that we get the 0 vector as our output when we combine them. Okay, any set of 3 or more two-dimensional vectors is linearly dependent. So if you've got 3 or more two-dimensional vectors, it's always linearly dependent. Okay, any set of 4 or more three-dimensional vectors is linearly dependent as well. Okay, so you need one more vector than the dimensional space that you're in order to ensure linear dependence. And I think that holds true. That would hold true in higher dimensions as well. Okay, so hopefully you found that useful. As always, if you're looking for any private tutoring or find this at all useful, please give us a thumbs up, leave a comment, and let me know how you're getting on. If you, again, are after some tutoring, you can find my details here. And good luck with everything you're doing, and I'll talk to you soon.